There we go. So mod 2, as it says here, it's statistics, A/B testing, and linear regression. So it's kind of completely different from what we were doing in mod 1, where mod 1 was very much like, making sure that we know how to code in Python, getting like the foundation down. We did a little bit of like data gathering, data cleaning, visualizations. Those are more part of like the analytics part. In mod 2, we get to go a little bit deeper because we start talking about statistics, the first part of which is probability. We get to A/B testing, which is actually a very common thing that data scientists do. We do A/B testing. A/B testing basically means like, all right, if I want to implement this new marketing strategy, I want to try like 2 different versions, A and B, just seeing which one is better. And then linear regression, which is going to be our very first machine learning model. So that's going to be very, very exciting. Linear regression, I think those of you who are like familiar with like econ might have heard of the word regression. But yeah, we're going to take a very, very different approach to it compared to like what you might have learned in an econ class. So the structure of mod 2 starts with probability, because probability sort of gives you that foundation for statistics. I think you have to understand a little bit of how probability works before we get into statistics. And after doing statistics for 7 sections, then we get into linear regression, because a lot of linear regression, I think I've mentioned this to some of you, but when we're running actual linear regressions, we don't actually have to like, put in formulas or anything. Python has built in, not built in Python, but there are modules and packages that we can import that does it automatically for us. So our job as data scientists is to interpret the model. And that's why we need statistics, because a lot of the weird numbers that the model is going to spit out at us, we need like some form of statistics to understand and interpret. So that's why it's important. Any questions on like the overview of the mod? Cool. I think worth mentioning is our final project for the mod will be a linear regression project, just so you all know. So cool. Because you will notice that there are a lot of labs in this section. I will honestly say that they're not all very, very important. So as we go through each section, I will point out what are the important parts to go through and which ones I recommend that you look at. For example, right now, section 11, I think just getting to at least the combinations part is like already kind of a stretch goal. Conditional probability, we will get back to in section 17. So I have a slide deck for this, and you'll see that I'm not gonna emphasize that conditional probability down as much this week. So we're gonna focus a little bit more on this first part, because I think that there are some pretty important concepts to understand there. But if you're really, really strapped for time, honestly, probability, introduction to sets, and intro to probability is probably all you really need for this section. Any questions on section 11 overview?
So how is it going to be connected to the first module?
Yeah, for the first mod, a little bit kind of hard. Well, the first mod comes back in and just like when you have to code things out for this section. So this section is really just like conducting a lot of statistical tests. Not this section, sorry. This whole mod is conducting a lot of statistical tests. The more probability ones, I'll actually say that I think because like you don't necessarily have to learn how to code a lot of these things. I'm sure some questions will come up during one-on-ones, but like, for example, when you have like a question, like, let's just take a look at the end of this. If it will load a little quicker. These exercises, these are probability questions. And I will say that coding it, learning how to like code out these questions, not as important. So if you want to just like take pen and paper and solve these problems, just do that, because I think being able to code this out is not that important for data science. It's just the main takeaways from these first few sections of the mod is really just conceptual. You just need to understand like how probability works. So if it's easier for you to use pen and paper, please do that. I'd say like don't waste your time trying to like, assign a bunch of variables to random things and like do the math like that. Sometimes for this kind of thing, I think pen and paper makes a lot more sense. Cool. Any other questions about an overview before we get into section 11? Cool. So these first half of mod 1, first half of mod 2, sorry, is pretty light on the coding. I think I've mentioned to some of you over 101s. So actually most of these study groups, I'll be just going through slide decks that I make for these sections. So we're gonna start with section 11. And let me just present this. Let me stop this share real quick, and then I can present with the presenter view.
One quick question. These slides will be uploaded, right?
Yeah, I will send out these slides for sure on yeah, I'll send out these slides on, I'll probably upload the PDFs to the lecture repo.
Yeah, that will be better, because like whenever we are referring, it will be good.
Awesome. Yeah. So I call this, well, this section is called Combinatorics and Probability, and I put in little brackets a crash course because I studied math in college, and this entire section was literally more than one semester of college. So I try to like, it is a lot of information. I don't expect any of you to like fully like understand all these mathematical concepts that I'm about to throw at you. For this section, this entire section 11, it's more of like understanding concepts rather than like being like, all right, I can solve this intense probability question. So very quick rundown of the things that we're going to talk about. What is probability and why we're doing probability in this course? We're going to talk really quickly about sets, permutations and factorials, combinations, conditional probability, and law of total probability. So the last two, I'll actually go way more in depth later in section 17, which is like, what, 3 weeks from now, 4 weeks from now. So that I'll just like introduce what it is, but won't go too in depth. I think the focus should be more on like the first 4 parts. So what is probability and also why? There's so many definitions of probability. I'm sure you've all seen like the probabilities questions of like, what's the chance of rolling a 6 on a 6-sided die? It's like 1 out of 6. What is the probability of flipping a coin and getting a heads? 1/2. So one of the many definitions I found was the probability of something occurring is its proportion of all possible outcomes. And so flipping a coin, all possible outcomes is you can get heads or tails. Probability of getting a heads, probability of tossing heads is just 1 out of 2 because there are 2 possible outcomes. The proportion of heads is just 1 out of the 2. In more mathy terms, it's the event space out of the sample space. So sample space is all possible outcomes. Event space is what you're looking for. So in like the probability of flipping heads, I just mentioned 1/2. The probability of rolling a 5. Your sample space for rolling a 5 would be 1, 2, 3, 4, 5, and 6, because this is assuming a 6-sided die. You have 6 possible outcomes. Rolling a 5 is 1 out of 6 of them. So why is it important to know probability? It is kind of the foundation of statistics, but also for data science interviews. Unfortunately, even though we don't like solve a lot of probability questions as data scientists, for some reason they like to ask them in data science interviews. I've gotten quite a few myself. And I actually, later when we talk about conditional probability, those are the most common interview questions that come out, and I will share like some of the questions that I've gotten in the past and just like the formulas for solving them.
So will the interview involve coding of probability or just answering the conceptual class?
It really depends. So very unlikely coding the probability. Like I've never gotten that before. I've gotten like timed interview where they send me like a link to a portal, and I have like 30 minutes to answer all these questions, and some of those questions are probability questions. Also, yeah, I've gotten the instances like, all right, given this kind of scenario, how would you solve for this problem? And then you, all right, I think are expected to bring up these probability concepts.
Okay.
Yeah, so that's kind of the why. It's less, I will say this section specifically is less directly used as a practicing data scientist, but it's just stuff that you're expected to know. So cool. So first, set theory. And the most important thing about set theory is just the terminology. So the labs go way more in depth on this, but I think the main things to take away from set theory is these three terms: the union, intersection, and complement. And also these Venn diagrams. I'm not sure how familiar people are with Venn diagrams, but basically what the Venn diagram, like the parts of a Venn diagram. So this square, this box that everything is in, is actually kind of relevant. You need to have like this box around the circles. So the box actually represents your entire sample space. So imagine like, I don't know, you have like 1,000 options there. Everything lives inside this rectangle. And then each of the circles represents a different event space. So in that case, if we want to look at like the probability of this left circle, let's call the left circle A and the right circle B. If I want to find the probability of circle A, it would just be the proportion of the rectangle that is the circle, if that makes sense. Please like feel free to interrupt me with any clarifying questions at any time. And so similarly, the probability of B is the proportion of the rectangle that is B. As you notice, the two circles, they overlap. So that means that there are some options that belong both in A and B. Let's use the example of like, all right, let's have this entire sample space be the outcomes of rolling a die, like one die. So 1, 2, 3, 4, 5, 6. Let's have A represent all even numbers. So A will be 2, 4, 6. B will be any number 4 or greater. So if A is 2, 4, 6 and B is 4, 5, 6, basically, I wish I could annotate on this better, but basically 2 will be in this crescent part. Do you guys see my mouse? All right, yeah. 2 will be in this left crescent part because 2 only belongs in A and not in B. The number 5 will exist in this right part because it only exists in B, not in A. And 4 and 6, because 4 and 6 exist in both, 4 and 6 will be in the middle. Yeah, I feel like it might have, I don't know, I did this in like high school, and it took me a while to like remember what all of these things mean. So yeah, just take your time and like letting this sink in. So basically, why that's important, why setting up this problem of like 2, 4, 6 and 4, 5, 6 is important, because we're going to use that to talk about this terminology. So when you have unions and intersections, you're talking about the relationship between two event spaces. And so when we say A union B, it means everything that is in A and also in B, or in A, anything that is in A or in B. So that means union is basically everything that's in both these circles. That was confusing, sorry you guys. But basically 2, 4, 5, 6, those four numbers are included in the union. And then when we have union, we also have intersection. So intersection looks at only the values that are in both A and B. So in this case, it will only be the numbers 4 and 6, because 4 and 6 exist in both A and B. And then now we have complement, and complement can be used in different ways. But the main idea of complement is like, it's like a negative. So let's say we want to take the complement of the intersection. The complement of the intersection is everything that isn't the intersection. So the intersection is 4 and 6. The complement of the intersection is 1, 2, 3, and 5. So it's just the opposite of whatever it is that you're taking the complement of. Cool.
Can you explain that again?
Yeah. So the complement is just the opposite of everything that you're trying to take the complement of. So for example, we can even take the complement of the union. So the union, as we talked about, has the numbers 2, 4, 5, and 6, yeah?
Correct.
So the union has 2, 4, 5, and 6. The entire rectangle has 1, 2, 3, 4, 5, 6. And so the complement is just this entire rectangle minus this union part. So that would mean the complement of the union is just the numbers 1 and 3. Yeah?
Sure.
Yeah, I understand this is a completely different part of the brain that you're using in the last mod. So it does take a little bit of an adjustment. But the labs do go way more in depth on this. Any other questions on like set theory? Because we're going to be moving on from this already. Cool. All right, so some quick terminology. I mentioned this earlier. Sample space is all the possible outcomes. The event space is one, it always has to be a subset of the sample space. And it's also based on the probability that we want to calculate. So let's say I wanted to calculate what's the probability of rolling an even number with a 6-sided die? The sample space would be based on that. So it would just be, what are the even numbers? So just 2, 4, and 6. There's also this that is a definition that came up in one of the Learn labs, which is the law of relative frequency. So this is when it gets a little bit philosophical and a little bit like more conceptual. But the law of relative frequency basically means that, well, I'll read it first. It's the probability the probability of an event, typo, I'll change that. The probability of an event is the ratio of positive trials to the total number of trials as we do an infinite number of trials. So let's say we want to find the probability of rolling a 6 on a 6-sided die. So where probability comes about and the concept of probability is, let's say you're rolling your dice like 20 times. The idea is you're not gonna roll a 6 exactly 1/6 out of 20 times. Does that make sense? So let's use a number that's divisible by 6, so it's easier. So let's say you're gonna roll the dice 24 times. Very likely you're not gonna roll a 6 exactly 4 times. Where the idea of probability comes about is if you were to roll a dice over and over and over again and in an infinite number of times, then the proportion of rolling a 6 is 1 out of 6 of all the times. So that's kind of where the concept of probability comes up. You have to like imagine you're like doing something over and over and over again. And then that number or that proportion is the probability. The proportion of times where you actually roll a 6 is that probability. It's a little bit like, I guess, philosophical, conceptual, but yeah. This is also known as the law of large numbers. If anyone has ever seen that phrase around, just know that that's also a thing.
So all the insurance companies use that.
Sorry, can Kishore, you say your question again?
Yeah, all the insurance companies use the law of large numbers.
Yeah. Actually, insurance is a very popular, like calculating like the risks is actually a popular interview question that includes probability. Yeah. Marv, you were saying something as well?
Yeah. Quick question. I just wanted to know. So would you say that all data science generally, or all like machine learning models or things like that, is all of that based on the law of relative frequency?
I will say some of them are. Okay. I think when we get to mod 3, actually, then we'll get to like take a deep dive into each model, but there are certain models that actually are based on probability. I think, actually, no, most of the models that we do end up using are more, they're more like mathematical algorithms. So not exactly, but in evaluating the models and in interpreting some of these models, there are some probabilistic concepts that, yes, take into account the law of relative frequency.
Gotcha. Okay.
I think that the next thing that we'll see this come back in is when we talk about p-values, if p-values means anything to anyone. There's sort of like sprinkles of the law of relative frequency in that.
Okay. Thank you.
You're welcome. Any other questions? Yeah, I'm fully aware that this is just like a lot of new information, so no worries. And like, yeah, any other questions that come up later, feel free to ask me at a one-on-one. Cool. So this part is, it might seem a little, as I explain it, it might seem a little, what's the word? I guess obvious, but these are actually really important probability axioms that like some mathematician back in the day said that, all right, these are the rules for probability. So first, the probability of an event is always between 0 and 1, because the probability of something happening is a proportion of something. So it can't be less than 0, cannot be more than 1. So that's the positivity axiom.
I'm sorry, could I ask
Yeah.
on that? So I'm not remembering which one, but on one of the lab problems, like they include, I'm blanking on the word, but like the sample space or like the list of possible outcomes.
Okay.
Is a event with a probability of 0 still considered in the sample space, or whatever the word is for list of possible events?
Yeah, so kind of yes, because the sample space at which you're looking at is always, well, sorry. You're saying like if the probability of an event is 0, is it part of the sample space? That's your question, right?
Correct.
All right. Technically, yes, based on like, I got this question before. I actually asked this question before, and they traced it back to some like philosophical logic of like how you like equate things. But the way I sort of think about it is that when you're asking for the probability of something, you're only asking that question to your entire sample space. And so if the probability of an event just happens to be 0, the event is still a subset of your sample space, but it's just an empty event, if that makes sense. It's kind of like a loophole in that, but it is technically considered part of the sample space, just that it's an empty set of the sample space. Does that make sense?
Sort of, I guess.
Yeah, it's not a clear answer. But yeah, technically, like if something, yeah, let's just go with that. Let's just stop it at like, yeah, it is part of the sample space, because let's say you're asking, all right, what's the probability of rolling a 7 on a 6-sided die? Technically, the question that you're asking that question to your sample space of 1 through 6. 7 is not part of the sample space. 7 itself is not part of the sample space, but you're asking the question from the event perspective. So 7 is not part of the sample space, but the event of like rolling a 7 is empty in the sample space. I don't know, that doesn't sound like
Got
very,
it. So
let
me try it. So I don't know, but I'm just
Yeah.
gonna try. So are you saying that when an event happens, let's say a 1 or a 2 is rolled, then that from a philosophical standpoint means that a 7 wasn't rolled? So then that kind of means that it's 0 in that aspect?
Kind of, yeah. Actually, yeah, that is, yeah. In the words that you were saying were correct.
Okay.
Yeah.
All
yeah.
right.
Yeah.
Okay.
I don't know too much of like deep probability and logic theory,
Sure.
but the words that you were saying were sound. I don't want to make any like big assumptions, or like I don't want to like tell you guys something that's like wrong. But
Cool.
these are axioms that are just like good to know. I personally like after I finished being a math major, I never nitpicked at them. So yeah, nothing to worry about. All right, so the second axiom is just what the definition of a certain event is. So certain is not just like, all right, we pick a certain set of this, but a certain event is like something that is certain. So in this case, this is if an event is equivalent to the sample. And so in this case, we're like, all right, what's the probability of rolling any number from 1 to 6? on a 6-sided die, that is a certain event because you know you're definitely going to roll something 1 to 6, and the probability of that is just 1. And then finally, the probability, the axiom of additivity. This one is a little bit confusing, but the probability of the union of 2 exclusive events. So actually, you know what? Let me draw this out here. I have like a whiteboard here that I can use. So let's see. I hope that this will be clear. All right. So imagine we have this Venn diagram. And here we have the union of 2 exclusive events. So the union of 2 exclusive events is, and we'll call this A and B. Does it appear flipped to you guys, or are you seeing it like A and B correctly?
You're seeing it A and B correctly, but then because you are
Can you not share
recording
the
will be
slides real
stop the
Oh,
screen, it will be.
good point. That's a really good point. All right, let me stop this share for a while. Thanks, you guys. All right, you guys can see this?
Yeah.
Perfect. All right, so here we have 2 exclusive events. And I'm just going to write here additivity, so we remember what we're talking about. So when we're talking about the union of 2 exclusive events, remember union just means anything that's in A or in B. So I'm just going to shade in A and B, because the union of these 2 exclusive events is anything in here or in here. And so the axiom of additivity is basically saying the union of this, the probability of the union of this is equal to the probability of this and the probability of this, as long as they do not intersect. So as long as the bubbles are separate, you can just add up their probabilities. So let's say the probability of this is like 0.3 and the probability of this is 0.2. The probability of the union of A and B is just 0.5. Gotcha? Thanks. I usually have like a tablet, but while I was moving, I forgot to charge it, so I don't have it right now. But next few study groups, if I ever need to do it, I have a better way of doing this. So let's go back to these slides. All right. So back here, just to like translate all of this mathy term, these mathy terms, the union of 2 exclusive events is equal to the probability, the sum of each probability, the sum of the probability of each event. So there's 3 parts here. Union of 2 exclusive events is equal to the sum of event 1 and event 2, only if the intersection is 0. So they do not intersect. Cool? And to counter that, what if they do intersect? This is actually not part of the axioms, but it's just a good formula to know that the probability of a union, if there is an intersect, is actually the sum of each probability minus the intersect. The idea of that is, if you imagine like, all right, these are the 2 probability bubbles. If they overlap, if you are counting probability A plus probability B, you're actually counting the overlapping part twice. And so you just need to minus their intersection once. Any questions? All right, cool. We're gonna take another turn of events here because we're gonna talk about factorials. So this section, after like starting this slide, is more of like counting theory. Actually a very, very interesting math topic, but also very confusing. I personally always get confused, so hopefully I'll like make things as not confusing as possible. But the first thing we're gonna talk about is factorials. So factorials, I don't know if anyone's seen like these excited numbers, but like anytime you see a number with an exclamation point, it's a factorial. And if you see like a number with a factorial, it basically equates to the product of all positive integers leading up to the number itself and including that number. So for example, if we're finding the factorial of n, we're just going to take 1 times 2 times 3 times 4, blah, 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 all the way multiplied by n. Smaller example, factorial of 3 is 1 multiplied by 2 multiplied by 3 is 6. Factorial of 4 would be 1 times 2 times 3 times 4, 24, pretty sure. So that's factorials. The probability use case that you would use a straight up factorial is the number of ways to arrange n objects. So I don't know, when I was young, I actually really enjoyed doing this kind of thing. So let's say you had like 3 letters, A, B, and C. What are the number of ways you can arrange A, B, and C? And it actually equates to 3 factorial. If you have 3 objects, it will just be 3 factorial. And if you like write out all the options, it'll actually come to like 6 options. So you can see here, ABC, ACB, BAC, BCA, CAB, CBA. And if you want, you can definitely try it on your own. I don't recommend it because it'll take a lot of time. But if you have more objects, like if you had like 5 objects, the number of ways you can arrange that will be 5 factorial. So that's like a probability use case of when you will just take the factorial of a number. And we're going to build on this in the next couple of slides. So after factorials, there's permutations. And so permutations usually comes along with combinations. And permutations and combinations are both counting methods that help us find the size of our probability spaces. So in short, permutation is just the number of ways to arrange k out of n items. So I guess to start, the formula is n factorial divided by n minus k factorial. I think it'll be easier to explain with a use case. And so in this example, we have, let's say there's a band with a catalog of 8 songs, but they have to choose a set of 3 songs, or they have to play a set of 3 songs. And how many different 3-song sets are there? And important to note for permutations is that a different order of the same songs counts as a different set. So let's say they have 8 songs. If they play like song 1 and then 2 and then 3, there's a different set from playing songs 3 and then 2 and then 1. So each of that counts. And this is when we take in the permutation formula to find the number of ways you can have like 3 song sets out of 8 songs. Is you're taking 8 factorial divided by 5 factorial. And it's 5 factorial because it's n minus k. In this case, n is 8, k is 3. So you're trying to make 3 song sets out of 8 songs, which is why k is the number of is the length of whatever the thing is that you're trying to pick. It's kind of hard to explain in like English words, but hopefully does this example make sense? All right, cool. But yeah, the way you would calculate it is just take 8 factorial divided by 5 factorial, which equates to 336. Another really interesting way to think about permutations is, as you can see, I put 336 is equal to 8 times 7 times 6. Let me just do this real quickly on the board here. So if I have, let's see, I'm just going to write this out. And then I have 5, 4, 3, 2, and 1. And I'm going to stop this share again to show you my whiteboard. All right, so if I'm taking 8 factorial divided by 5 factorial, as you can see, 8 factorial is the product of all numbers 1 through 8, and then 5 factorial is product of numbers 1 through 5. If we remember our division, I know it's been a while since we did fractions, but remember how we can cancel things out? So here I can cancel out the 1s, I can cancel out the 2s, I can cancel out the 3, 4, 5 because there's 3, 4, 5 here. That makes sense? And that's how we end up at just 8 times 7 times 6. And so another way of thinking about permutations is you actually count backwards k times. So in this case, k was 3 and n was 8. So we'll just start from 8 and then count back three times, or like count back to 3 numbers, 8 times 7 times 6, and that is the number of permutations of picking 3 from 8. Questions on that? like I can tell you in college, I spent like an entire week on like permutations. So I don't expect you all to like be like permutation gods in like 10 minutes. But cool. Because the next thing after permutations is something very similar but completely different. Combinations. So in combinations, it's the number of ways to choose k out of n items. So kind of similar in that sense.
Screen.
Oh, sorry. Oh my gosh. That's a really good reminder. Thanks, Kishore. All right, combinations. It's a number of ways to choose k out of n items. And in this case, the order of your items doesn't matter. And so remember how I said, like, if I played song 1, 2, 3, and then songs 3, 2, 1, if we're looking at combinations, they would count as the same thing. So in this case, the order doesn't matter. We're looking for unique combinations. So the formula is a little bit different. It is n factorial divided by the product of n minus k factorial and k factorial. This is a formula that like me after like 2 years of learning this finally memorized. So like you don't have to remember this at all. But an example is, let's say I have like 8 different seashells and I want to randomly pick 3 to give away. How many combinations of 3 shells are there? And so like just plugging it into the formula, there are 56 different combinations, 56 different 3 shell combinations that I can just randomly give someone. Does that make sense? So the difference between combinations and permutations is that if this was a permutation, I would care like the order in which I'm picking out the seashells. But in this case, I don't care.
So one quick question. So now it's, if it is going to be 8 divided by, let's say factorial, in factorial itself, like if I just remove the factorial factor, it's like 8 divided by 5 multiplied by 3, that's 15.
So not exactly. It's actually divided by 5 factorial times 3 factorial. So it's not really 15.
Okay, so it will be like 5 minus 3. So that's like 5 and 4. That's 20, correct?
Yes, yes, exactly. Exactly.
5 and 4 factorial, and then here it will be 8 factorial.
Yeah, yeah. I think so. Yeah, I think so. I mean, if we write it out and you like can do a bunch of canceling out, you'll see what it becomes. But yeah, usually like the way I used to remember, because I used to get confused between permutations and combinations all the time. I would just remember that combinations, you end up with a smaller number. So depending on the context of the problem, sometimes that helps. Like I know the upcoming labs on permutations and combinations, they're just having you solve permutation and combination questions. And so that's something that I sort of use to remember which one I want to use. All right. I know this is a marathon of a study group. All right, let's take a look at what comes next. All right, these last 2 slides, I'm just gonna be introducing concepts, but we're not gonna get super in-depth because we're gonna get to conditional probability in like 3 weeks, section 17. So conditional probability, the idea of conditional probability is finding the probability of something occurring given that something has already happened, which is an important concept for Bayesian statistics. And Bayesian statistics is, I would say, like pretty important. We'll come back to this in section 17, so I don't want to talk too much about this, but it's good to remember the formula. So here we have this Venn diagram, and let's just say we want to find the probability of A given B. So the notation for conditional probability, let's say we have A and B. The notation is there is this like straight vertical line, and everything before that line is the probability that you want to find. Everything after that line is what has already happened. So in this case, and the proper words that we use in math are like given that. So here we're finding the probability of A given B. So in this case, we're assuming that, all right, B has already happened. And so the idea of conditional probability is our sample space has been reduced to only B. That to me is how I understand it. If through your readings you have a different way of interpreting it, that works as well. But the idea of this is B is now our new sample space. And we just want to find the probability of A that is within B. And so the formula of that is to find the probability of A given B, we're dividing the probability of both A and B over the probability of B. And I'm going to explain it with this diagram. I think it's a little bit clearer with this diagram. So let's say blue circle is A, green circle is B. So given B, so B has already happened, what is the probability of A? So given B, so B is now our new sample space. What proportion of B is A? So that's why we're taking this little intersect part divided by the whole of B. That makes sense?
So can we put it in numbers? So let's say A is 10 and B is, let's say, 8. Okay.
All right, let's use the same like dice examples as before. So bubble A is 2, 4, 6. Bubble B has 4, 5, 6. And so we know this intersect has the numbers 4 and 5. Sorry, the intersect has the numbers 4 and 6. In here, yeah. In here, in this like left crescent, we have the number 2. This right crescent, we have the number 5. And so conditional probability will be like, all right, what proportion of B is the intersect? So B only has 4, 5, 6. And the part in the intersect is 4 and 6. So the probability of A given B is 2/3. Yeah. That's a good clarifying question. I should have definitely like used like actual numbers in here. But yeah, I do think that the labs explain these like foundational concepts pretty well as well. It just sometimes can get a little technical, but feel free to clarify anything with me over Slack or during one-on-ones.
Quick question, Yish. So just for clarification real quick. So the actual diagram, is that always going to be the case that the event that happened is going to be the unfilled circle and the one that hasn't happened is the one that's filled in?
No, that's so like the coloring of the diagram has nothing to do with the question. Yeah.
So it could definitely be switched around. Okay, got it. Okay.
Yep, definitely. But yeah, we're gonna get back to this later. But cool. Now this one is even more intense. I don't know why they put this in section 11. I feel like it's definitely more relevant in section 17 because there's a lot of like stuff that is assumed that you know here. But imagine this is our Venn diagram. So this lower one, I know it's a little confusing because it's not just bubbles anymore. But basically what they did is they took the entire sample space and just split it into 4 rectangles. So there's like A1, A2, A3, and A4. And A1, 2, 3, and 4 add up to our sample space. And then on top of that, overlaid on top of that, there is B. So the law of total probability is if you don't know what B is, but for some reason, you know the probabilities of B given A1, B given A2, and B given A3, and technically B given A4, you can find the probability of B. So for example, let's say you know that the proportion of A1, that is B, let's say like this orange part divided by this A1 square is maybe like 0.2. So let's say this orange part is 0.2 of this whole A1 square. For this A2 square, maybe this B is like 0.8. And then for this part, it is like 0.5 or something. If you just add them together and do a little bit of division again, there's a formula that's on the labs, but basically it's saying that if you know the proportion of the A's that is B, you can find the probability of B overall. This is not important at all right now. I just put this here because it's part of section 11, but I will come back to this for sure with like a worked example in section 17, where I think it's a lot more clearer after you guys have had like a little more experience, like working with probability and statistics. We'll come back to it. But yeah, that is everything in section 11. There are some parts that I didn't really talk about, like especially, I think the part that a lot of people get tripped up on is in the labs, there are a lot of permutation questions, and there's the idea of permutation with repetition. I challenge you all to like try and figure it out on your own, and then if not, feel free to ask me during one-on-ones. But yeah, any questions for me regarding section 11 so far?
So the labs that are important are till the first
Yes.
first 7.
Yeah, I would say like the prime, please do these. I would say like 1, 2, 3, 4, 5, 6, up to introduction to probability. That's just to like get an understanding of like probability as a concept. And then, because really permutations and combinations come in, honestly, interview questions. And then also, let me just double check this real quick. A little bit in section 12, but not super important. But anyways, yeah, definitely like the important ones you want to focus on are the first 6. Permutation and combination is just going to be a lot of math questions. So please feel free to do these like on pen and paper. No need to like code it out, because I think the coding out part like takes up a lot of unnecessary time. Conditional probability is actually extremely important, but I just think that it's worthwhile like taking more time and like letting probability concepts sink in first before diving into conditional probability, because we do come back to it in section 17. These words might not mean anything to you right now, but it is all conditional probability stuff. Any other questions?
Not so far.
Okay, sounds good.
Okay.
Yeah.
Okay. I just remember. So this the project here is going to be about linear regression. So that will be like more important, and which comes only after, let's say, we are around 15 and 16 section.
Linear regression really starts at 18.
Okay.
I can tell you right now that like section 11 will not be a part of your project.
So, but like we still need to have the concept clarity.
Yeah,
bring
that's right.
water.
Sorry guys, like a full day of project review. So any other questions?
That should be fine.
Well, awesome. Thank you all. I will post this recording once it's done processing. I think I actually have like most of your project reviews done, which is exciting. I mean, I just have like 2 or 3 left. But yeah, have a good rest of your night. Slack me if there are any questions as usual.
Sure.
All right. Bye everybody.
Bye. Thank you.
You're welcome.
Thanks, Yash.